Well, Ashley is with us. Good going. This is October 1st. And my watch said it was October 31st. But there's only 30 days in October, so I had to fix that. Hey, look at here. Ben's with us, Darren's with us, and Ashley's with us. We've got a class. And we have 3 minutes before class starts. Did you guys have any questions for me? Well, let me write down your homework that's going to be due. I was just looking that up, and it looks like tomorrow homework number 13 is due. Chapter 4, number 3. And I need a diagram. If you don't have the diagram, you're not going to get a 4 on your homework. And that's due tomorrow, which is Friday. And then homework number 14 is 471, and that's due Sunday. That's dealing with thermal expansion. I talked about it a little bit, but we probably should talk about that a tad more. Okay, here's your chance. Did anybody want to ask me anything? Well, what are we going to study? Let me write down the topic. We're going to do some more of this what do they call it? Statically indeterminate. Yeah, that's what we're going to do. We're going to do statically indeterminate problems. Okay. Well, let's is it time? Oh, yes, it's time. Here's your last chance to say anything. Go ahead. Well, nobody said anything. Now let me see if we've got some more customers here. Oh yes, we've got Braxton and Ben, Alex, Ashley, and Shane, and Nicholas and Darren. We've got a good crowd. All right, well let's review this business about thermal stress, and we'll get back into this statically indeterminate in a minute. The equation, they really should call it thermal deformation because it goes like this. And here, I'll just make us up a problem and do it. Suppose you had some fixed walls here, and you had a rod made of A36 steel. Suppose the diameter is was, I don't know, inch and a half. I'm just making this up. And suppose it's 3 foot, 3 foot long. And suppose you install that, and I don't know, you could weld it, I guess. Some kind of connection there. Glue it, weld it, bolt it somehow. And let's say the temperature goes up. Say there's a change in temperature of, I don't know, we'll make something up, 25 degrees Fahrenheit. Because we're dealing with inches here and feet. We ought to be doing with Fahrenheit, right? Gosh, that's a big increase, but really not that big because what was it this morning? 50? And if you got 25 degrees hotter, what would that be? 75? Yeah, you can have a 75 or 25 degree temperature increase here in Oklahoma. Just no problem. Well, let's see what'll happen. Well, you know what's going to happen? It's going to try to expand. But if these are solid walls that can't move, you're going to have forces that are pushing on them, right? That makes sense. And we're going to find what that force is. Okay. Well, we're going to have to look up this alpha. Go in your book. It's in the back page, and you want to look it up for U.S. customary, and it says 6.6. Let me write that down someplace. It's 6.6 times 10 to the minus 6 per degree Fahrenheit. That's what it says. All right. Well, look here, we know alpha and we know delta T, it got 25 degrees hotter. And we know L, hey, we could find out they put a little T there, the thermal deformation. I'm going to shut up for 20 seconds. I'll get my calculator out and I'm going to figure the thermal deformation. You go ahead, and then I'll call on one of you. Go ahead, do it. Find the thermal deformation. Okay, I found the thermal deformation, and I'm going to call on my friend Shane. Shane, unboot. That's the wrong word. On something. You know what I mean, Shane?
Can you hear me?
There you go. Shane, what'd you get for the thermal deformation?
Was the length of that? Is that 3 foot?
3 foot.
Around.
3 foot.
Well, sorry.
0.000495.
That's what I got.
So they're doing a briefing for the medical. They're going to start that COVID.
Here, let me mute everybody. But you guys can unmute anytime you want. And feel free to do that. Okay, now here's the problem. According to this thing expands, not much, not very much. You could convert that to inches if you wanted to. Let me do that just for kicks. It's in inches, it's 0.00594 inches. You know what it is? It's close to 6,000ths of an inch. Well, you can measure that. 6,000ths of an inch. They have micrometers that will measure 6,000ths of an inch. But see, this thing cannot expand. So what happens is you build up this force here and you have a normal deformation equals to 6,000ths of an inch. That in a way you could think of it as pushing it back 6,000ths of an inch. And so let me write that. There's your homework. You can read that in the on your syllabus there on Blackboard. See, here's what we're going to do. This is the normal deformation. It's going to be, remember, we cooked up this formula. I showed it to you, cooked it up from scratch. What we're going to do is we're going to make a normal deformation that's negative, that'll push it back exactly 6,000ths of an inch. Yeah. So it doesn't really go anyplace. But let me write that down. Well, that's what that F is. So you could put an F there if you wanted to. Yeah. So we have what this is. We probably should put it in feet. At 0.000495 feet. I don't know if that shows up on your board or not, on your computers, but anyway, we know what it is. And that's going to equal F times 3 feet divided by the area, which is be pi over 4, 1.5 inches squared times E. Oh, we're going to have to look up E. Go to the back. We want the one for English or U.S. customary, and it's 29 MSI. This value here is 29 MSI. Now we have a teeny tiny problem here. No, we don't. There is no problem because the square inches will cancel with the megapounds per square inch. Everything is just fine. And so you'll have feet on the right, feet on the left. Here, let me do it this way. I'm going to put this 0.00495 feet here on the right. And we have this equation. Let me box it up for you. See, what this is the normal deformation, and it really is negative. See, if you take the negative and the positive and add them together, you'll get 0. I probably should have written it like this. The thermal deformation plus the normal deformation equals 0. But see, the normal deformation is negative. I just scooted it to the other side of the equation, and I'm just looking at the absolute value. So here we have an equation, and I want you to find what this external force is on our rod there because it heated up. It's pushing on the walls, and the walls are pushing back. I'm going to shut up. You have a minute to find that force for me, that normal, external normal force. Go for it. Why am I looking at my phone? I need my calculator. Okay. Okay, I did that, and I've got I just need room to write here is my problem. There's a little room in here. I've got my value for this external normal force. Let me ask my friend Samuel. Samuel, unmute, please, and say hello.
Hello.
Hello. Samuel, have you got that force yet?
I got a force of 84.56 kips.
That's what I got. Good going, Samuel. Proud of you. The force is 84.56 kilopounds. Yay, Samuel and I are doing great. Now I want you to find the stress. See this little guy here, that's the symbol for stress. The chapter we're studying calls it thermal stress. If you want to put a little T there, that's okay. I'm going to shut up. I want you to find the thermal stress. We know the force and we know the area. So do it. Go ahead. I'm going to do it. You do it. Find the stress. Well, I think I've got the normal stress. Let me ask my friend Nicholas. Nicholas, unmute Nicholas, please, and say hello. Earth calling Nicholas.
Hello.
Yeah, hey Nicholas. Hey, did you get that normal stress yet, Nicholas?
No, I got kind of lost there for a second.
Well, just divide by the area. Here's the area. Pi over 4 times 1.5 inches squared. That's what it is. Take your 80.
47.
Say again.
47.
That's right.
5. But I think we messed up on the deformation. Wasn't the deformation? I think we left that at 0.
Double check here. You could be right. You could get a thank you point for this, Nicholas. What Nicholas is saying?
Well,
Nicholas, you're saying this is wrong here? Oh, no. I need another 0 here, don't I, Nicholas?
Yeah.
I can see that right now. Nicholas gets a big, fat thank you point, and there's supposed to be another 0 there, and I didn't have it. So now we're going to have to do this again. Will that make the force smaller? I think so. I bet it'll make it 8.4. What do you guys think?
That's
8.4.
That's what I got.
I was wrong and Nicholas was right. Okay, now that we have the force right, thanks to Nicholas, now let's do the stress. That'll make the stress smaller too. Nicholas, do you have the stress now?
Well, it'd be 4.785, right?
Oh, well, I got 4.782, but let's don't fight over that 5. But what's the units?
Uh, thousand pounds.
No, it's not in pounds. Stress is not in pounds. Stress is not in pounds. What is stress in, Nicholas?
You got me on the units again. I don't know.
Well, you are truly blessed because you're going to find out what stress is measured in this morning. It's the most important thing in our course, and you're going to learn that stress is measured in PSI. Now, if you have 4,782, that would be PSI. You knew that though, didn't you, Nicholas?
Maybe.
You knew that stress was in PSI, didn't you?
Wait. You got kips divided by the area. So you got thousands of pounds per square inch divided by square inches.
Well, you can go 4.782 KSI if
Oh,
you'd
kips.
rather,
Okay,
but all that is 1,000 PSI.
Yeah. Okay, I got it now.
Now, did I do that right? Because if I didn't, I could give somebody another big fat thank you point. Anybody else getting 4.782 KSI?
I did.
Hey, well, I think we did that then. Good. And Nicholas found out what stress is measured in. But now that's in the American customary. In the metric, it's measured in well, it's usually kilopascals. It's measured in kilopascals. Well, I'm going to erase this if everybody's happy. Unless you have a question, I'm going to erase that. And we'll be doing some statically indeterminate problems. Well, okay. Let me erase that then, if you're happy. Now, let me just comment on this kilopascal business. I get students that write this all kinds of ways. They go capital K, little p, little a. Well, that's wrong. They go capital P, big A. That's wrong. There's a lot of ways to do it wrong, but it's a little k, it's a big P, and it's a little a. That's the correct way. Do it the correct way. Do it the correct way. You know what little k stands for? Little k stands for kilo, which means 1,000. Big K does not stand for kilo. In fact, it stands for Kelvin. It's a temperature, an absolute temperature. So do it right. Quit doing it wrong. Okay, well, let's, anybody have a comment before we tackle a statically indeterminate problem? We're going to do problem 433 now. I got this window up here with a picture of me on it. I don't want that. I don't know whether you guys can see that or not. We're doing 433. It's in your book here someplace. Let me see if I can find it. It's on page 149. Now they have some A36 steel pipe with an aluminum core. So here, I'll draw it for you. The core is aluminum. And then they have a steel pipe going around it. The pipe is made out of steel. Well, let's look up some stuff for that. Go to the back, and aluminum we're in the metric system with millimeters and kilonewton. So we don't want the English, we want the metric stuff. A36 steel, the aluminum, this particular alloy of aluminum is 68.9. I'm trying to write down the modulus of elasticity. Is that right? No, it's gigapascals. That's wrong. All right, I did that. While we're at it, let's get the area of the aluminum. Now, the area would be pi over 4. Now, they gave the radius, didn't they, or the diameter? Yeah, they said the diameter is 80. So, well, that's the outside diameter. Inside diameter is 70. So it's pi over 4.070 meters squared. That'll give you the area. Now let's do the steel. The steel, the modulus of elasticity is 200. I'm looking this up in the back of the book. Can you find it? So see if you can find those. Now we're going to get the area of the steel. And we'd probably put a subscript there for the aluminum. The area of the steel, you're going to have to go pi over 4.08 squared minus 0.07 squared. Okay, great. I wonder if I did all that right. I think so. All right. Here, let's go ahead and get those. Go ahead and do those. I'm going to do them, and we'll compare notes here in a minute. Go for it. Now I'm going to do this one. And I want you to double check me. Okay, we did all that. And if anybody got what I got, I want to hear them say, uh-huh.
Uh-huh.
Yeah, there's an uh-huh. How about another uh-huh?
That's what I got.
Yay, there's another one. I think we're doing great. Now let's put these forces on here. Now, somehow, I don't know how they did this. Maybe they welded a plate on both ends. But somehow they're applying a force of 200 kilonewtons. (200 kilonewtons to both ends. 200 kilonewtons to both ends there. Notice the little k. It's not a capital K. It's a little k. Little k stands for kilo. And here's our statics equation. Our statics equation goes like this. The force of the aluminum plus the force of the steel equals 200 kilonewtons. That's your static equation. See it? Force of the aluminum plus the force of the steel equals 200 kilonewtons. Does that make sense to everybody? See, the aluminum is supporting part of the load, and the steel is supporting part of the load. And together, they're supporting 200 kilonewtons. But you can't solve that. Not with statics alone. But see, we're in strength of materials. And you can solve that with something we call the compatibility equation. In this case, the compatibility equation is real easy. It just goes like this. The deformation of the aluminum is going to equal to the deformation of the steel. I mean, the aluminum is going to stretch. It's going to get longer. And guess what? The steel is going to stretch exactly the same amount because they're together. They're bonded together somehow. So that's got a fancy name. They call it the compatibility equation. Compatibility equations always involve deformations, and I want to warn you, they can be kind of tricky. But this one, it wasn't tricky. This was pretty easy. And now we're going to write that equation. We just need some room to write it in. How about down here someplace?
Mr. Griffin?
Yes, I'm listening.
How do you find this compatibility equation?
Mohammed, it's difficult. But in this case, it wasn't for me because I know that this body here, this structure is going to stretch. And they stretch together, see? They don't stretch separately, they stick together. So however much the aluminum stretches, gets longer, the steel stretches, gets longer the exact same amount. Does that make sense?
Yeah.
That's it. In this case, it was pretty easy. It's not always easy, though, let me warn you. Okay, now we're going to write we're going to write it out. You know what that's equal to. That's equal to, well, here, let's just write it like this. That's equal to the force of the aluminum times the length, which they give it to us. It's 0.4 meters. I don't know if I ever told you that, but this thing is 0.4 meters long. And then the area of the aluminum is 0.00 blah, blah, blah. Let me write that down. 0.03845 meters squared. And the modulus of elasticity for aluminum is 68.9 megapascal. That is the deformation of the aluminum, and that is equal to the deformation of the steel, which is the force of the steel times the length, which is 0.4 meters.
Mr. Griffin, and that's gigapascal. 68.9, it's a gigapascal.
Hey, we have another big, thick, thank you point. That was wrong. And Mohammed helped us. Thank you, Mohammed. It's
You're
giga.
welcome.
It's giga. Okay, now on the steel, the area of the steel is 0.00111781 meters squared. The modulus of elasticity for the steel. I don't know if I ever wrote it down. Go back and look it up. I think it's 200 gigapascals, but we better look it up to be sure.
It is.
It is?
Yeah.
See there? I remembered that. Okay. Well, here, let me, I just need a little room here to operate. Remember, we had this equation here now. Force of the aluminum plus the force of the steel is equal to 200 kilonewtons. You know what? We have two equations and two unknowns. Here, I'll box them up for you. Look at there. Hey, look, there's an equation. It's got two unknowns in it. Oh, look, here's an equation. It's got two unknowns in it. They're the same unknowns. We have two equations and two unknowns. We can solve this. Two equations, two unknowns. We can do it. See, before all we had was this one equation with two unknowns. You can't solve that alone. We need another equation. The other equation is called the compatibility equation. This is it. See, the compatibility equation says that the deformation of the aluminum is equal to the deformation of the steel. All right. What I'm going to do is I'm going to do some algebra on this equation here and see if you can agree with me. First of all, I don't need that 0.4. I can get rid of that. It's in both of them. I'm going to do a little algebra on that. And here's what I'm going to do now. I'm going to say the force of the aluminum is equal to, let me put these numbers in just a minute. I'm getting the force of the aluminum is equal to 1.1254 times the force of the steel. Can you get to here from here? You guys, I'm going to give you a minute to work on that. See, here's this equation here. They both have gigapascals, so you can just forget about the gigapascals. You don't need to multiply by 10 to the ninth and multiply it here by 10 to the ninth. You can just lop it off. Just see, like that 0.4 meters, we don't give a rip about that 0.4 meters, do we? And the gigapascals, just forget it. I know that you can get to here, but go ahead. I'll give you a 30 seconds. Make sure I did that right. Did anybody get this equation here from this equation here?
Yeah, except 5.3 on the end, except for 5.4. But I mean, that's just a rounding error. So
It is 5.3. You're right. I think I just rounded off. Yeah, we're happy. Hey, we're almost through now because see, look, I can substitute that value for aluminum in here. Is there enough room? Let's see if there is. Yeah, there's enough room. See, if I substitute that in there, I have 1.1254 force of the steel plus the force of the steel equals 200 kilonewtons. And we all took algebra and we can solve that and we can get the force of the steel. I'm going to shut up. I want you to solve it. Go ahead. I'm getting the force of the steel is 94.1 kilonewtons when you plug that in. And I'm waiting for an
mm-hmm.
Yeah, there's one. And now you can get the force of the aluminum. All you got to do is multiply that force of the steel. Is there room here? Not much, but there's enough. The force of the aluminum will be multiplied by 1.1254. I'm getting a 105.9 kilonewtons. Now, if you add these two together, do you get 200? You know what? I think you do. It looks like the steel is supporting 94 kilonewtons, and the aluminum is supporting 106 kilonewtons. But that's not what they want. They want the stress. I'm going to make some room here someplace. We'll just make us some room. Here we go. They want the stress. Well, the stress in the steel, that's going to be the force of the steel divided by the area. That's how you get stress. You take the force of the steel and you divide by the area of the steel. Uh-oh, did I erase it? No, I didn't. It's right there. And then to find the stress in the aluminum, you take the force in the aluminum. See, this was, you divide by the area of the steel, and here you divide by the area of the aluminum. All right, I'm going to shut up. We've got the forces, and we have the areas. I might have erased part of them, but I can find them here. That's the area of the aluminum right there. And that's the area of the steel. Find the stresses for me. I'll be quiet. Go for it. Well, those are what I'm getting for the stresses. I wonder if anybody's getting that. If so, say uh-huh.
The same for aluminum. I haven't done steel yet.
But take your time. Take your time.
Yep.
I think I heard a yep.
Yeah, that's what I'm getting.
Yay, I think we did good. Now, guys, there's one last check here. We've got to see if these things went plastic or not. We're going to look up the yield strength for steel. Well, you go to the back, and it says here the yield strength for steel is 250 megapascals. Well, what we've got is 79 megapascals. We're nowhere near yielding. So it didn't yield. Now let's look up the yield strength for aluminum. Okay, I'm looking it up now. And it says 30, no, wrong page. It says 255 megapascals. 250. Make sure you can find those. They are in the flap of your book. You know, the back flap of your book. See if you can find those. Now the question is, did the aluminum yield? Well, no. 27 is nowhere near 255. So they did not yield. See when they yield, it's kind of like, well, it kind of goes like butter. It just kind of take a stick of butter and yank on it, and it will yield real easy. And that's what steel will do if you have stress bigger than the yield. Okay, now let's look at the answer. 433, we'll see what they said for the answer book. 433. They're pretty good. They're right 99% of the time. This answer book, they said the aluminum is 27.5. Hey, that's what we got. Yay, we got the same thing. Megapascals. We're doing problem 433. And they said the stress in the steel is 79.9 megapascals. Hey, they just rounded off. We got 79.87. They got 79.9 megapascals. We agree with them, and we understand that problem. We just did a statically indeterminate problem. To solve it, we had to write a compatibility equation, and that's what this is. This is a compatibility equation. Are there any questions? Well, okay. I guess you're happy then. Good. Excellent. We'll do another one now. I'm going to do another one here. Let me find the one I want. This one's on page 175. See that problem there, that was under tension. We were stretching. But this problem we're going to do right now is under compression. We are compressing. And it's problem 4103. Let me put that up here. I'm going to erase all this if you're happy. All right, that was good. That was wonderful. And we've had a couple of students that really helped us out here this morning. I forget who it was and what they did, but I appreciate them. This is problem 4103. There's a black rectangle on my board there. Let me write this where it doesn't get in the way of that black rectangle. 4103, and it's on page 175. And what they have is, it's aluminum and steel again. Yeah, I think it's a different kind of aluminum though, huh? Yeah, it's a different type of aluminum, but it has A36 steel core. Well, here, let me draw it. They've got an A36 steel core. And it has a radius of 1 inch. Okay, it's got a radius of 1 inch radius. And then they have an aluminum sleeve. Is that what they call it? Well, they don't call it a sleeve, but I'm going to call it a sleeve. And it has a radius of 2 inches. So it's kind of out here. See, it's got a radius of 2 inches. And it's aluminum. Artist's rendition of the situation here. So you got a steel core and an aluminum sleeve. And then what they start to do is, this is sitting on the ground. This is just sitting on the ground. And somebody comes along and gently starts putting a heavy weight on it. Did they tell you how much weight? Yeah, 300 kips. They put 300 kips on it. You know what that is? That's 300,000 pounds. Gosh, that sounds like a lot to me. They're going to put 300 kips, 300,000 pounds. What is that, like about 100 pickup trucks? Man. Okay, well, that's gonna compress this thing for sure. And here's our static equation. The force of the steel plus the force of the aluminum will equal 300 kips. That's your static equation, but you can't solve it. We have no idea what they are. We're going to find out, though. Did I get that right? Yeah, everything's right. Now we need to we need to look up the modulus of elasticity for the steel. Okay, I want to find out if you guys can find this. Let me ask one of my students. How about my friend Julian? Julian, unmute and say hello, please.
Hello.
Yeah, there he is. Julian, can you find the modulus of elasticity in the very back page of the book? It's the flap, the back flap. Modulus of elasticity for steel with the U.S. customary units. Julian, what do they say?
Give me 1 sec, please.
Hey, take your time, because other people are trying to find it too, and we all need to know how to find that.
I have the online.
Yeah, it's
Mhm.
kind of hard to find. Take your time, Julian. We all need to know how to find that. I got a suggestion. Why don't you guys somehow, if you can get access to a copier, copy off those back 2 pages in the flap of your book, and you'll just have it for you. Just take that paper out and you can look stuff up. Don't you think that's a good idea? Make a copy of those last 2 pages. We're doing A36 steel. I think that's what they said. Yep. Julian, are you having any luck?
No, not yet. Sorry.
That's fine. Don't worry about it. We've got to know how to do that.
And then 200 gigapascals.
Yeah, now that would be right if we were with meters and newtons and all that kind of stuff. But see, we're in inches and pounds. We're using the U.S. customary units. Can you find that table for the U.S. customary units? You found that back flap. You got
I'm actually just using
But it's-
Google. I usually like use Google to find all these instead of hunting through the book. I don't know if that's like
That's okay. Well,
okay.
Google it then.
Okay, 29,000 KSI.
That's it. Now, the way I write that is 29 MSI.
Yeah.
29 MSI. Now, while we're at it, let's write the yield strength. Now, the yield strength, this is A36 steel is the name of it. It's structural steel. It's the alloy that has the biggest modulus of toughness. That's what you want to build your bridges out of. And the yield strength for A36 steel is 36 KSI. Hey, I wonder if that 36 KSI has got anything to do with the name of the steel, A36 steel. What do you think? Yeah, you know what? That's where they get the name A36 steel. It's got a yield strength of 36 KSI. Now, while we're at it, let's get the area. Now, the area of that steel, now we've been using pi over 4 d squared, but here they're giving us the radius. So you'd want to go pi R squared, 1 inch squared. And I'm just getting pi square inches for the area of the steel. Now let's do the aluminum. Now the modulus of elasticity for the aluminum, and my friend could Google it again, or it would be good if you guys could find this table too. But I want somebody out there. We got a lot of students. Now let me pick on somebody in particular here. How about my friend Darren? Darren, unmute and say hello, please.
Oh,
Yeah. Hey, Darren, can you find the modulus of elasticity for aluminum with the US?
yeah.
Or what does it say?
I was literally just looking at it. I put my book down for a second. Oh. 10,000, or I'm sorry, 10,600 KSI. Ugh.
Yeah, that is correct. It's 10.6 MSI is how I would put it, but what you said is correct. And do you know what the yield strength is for that aluminum?
The yield strength is for 60 KSI.
It's 60 KSI. Good going. Now let's get the area of the aluminum. Well, that's just pi r squared. The only thing is that the radius of the aluminum is 2 inches, but see, you have to subtract the 1 inch because the steel is taking up the middle. And so what you wind up with is 3 pi square inches. I hope I didn't lose anybody. Y'all, little Southern talk there. Y'all happy with that? Okay, well, we're ready to write our equation then, our compatibility equation, because see, you can't solve it with this equation alone. We need the compatibility equation. Okay, well, let me write it. Here, let me scoot this up here out of my way, because I need the room. Well, I've got some room now. I think I could probably put it in this space right here. We're going to write the compatibility equation. And again, it's just the deformation of the aluminum is going to have to equal the deformation of the steel. They're both going to have to compress the same. Now, the deformation of the aluminum is going to be the force of the aluminum times the length. I don't know what the length is, but it's going to cancel out anyway. Divided by the area, which is 3 pi square inches, times the modulus of elasticity, which is 10.6 MSI. We're done. That's the deformation of the aluminum. That's going to have to equal the deformation of the steel, which will be the force of the steel times the length. See, we're talking about this length right here. I don't know what it is, but it's going to cancel out anyway. Divided by the area of the steel, which is pi square inches, times the modulus of elasticity, which is 29 MSI. Guys, we've got 2 equations and 2 unknowns. Here, let me box them up for you. There's our 2 equations. See this one here? That's the statics equation. This one here, that's the compatibility equation. Now we're going to solve those. I need a little room to operate, so I'm just going to sacrifice some of this here. I need some room, so I'm going to say, I think I can reconstruct those. I'm going to do a little algebra now. What I'm going to do is I'm going to say the force of the aluminum is equal to $1.09655 times the force of the steel. Can you get from this compatibility equation to this right here? Can you make it? I'm going to wait for an because I want to make sure I got that right. I took this. I just lopped off the L's. I don't need those stinking L's. Get rid of them. The MSI is the same on both. Just forget it. Even the pi's. I got pi's down here. Algebra says I could get rid of those pi's. Can you get to here with me? Somebody say,
Did get that.
Was that an
Uh-huh.
Yeah, there's one. Give me another
Sure.
Yeah, there's a sure. That'll cut the mustard. Okay, guys. Now what I'm going to do is I'm going to substitute that in here for the force of the aluminum. And here's what we'll say. We'll say the force of the steel plus 1.09 blah, blah, blah times the force of the steel equals 300 kips. You see what I did? I substituted the force of the aluminum. I stuck that in there. And now I can solve this. Here it goes. I'm going to solve it. I'm getting the force of the steel is 143 kips. And I'm waiting for an on that.
That's what I got.
Yay, there's somebody. Now we're going to get the force of the aluminum. We'll just multiply by that number times the force of the steel, and we'll get it. Here goes. I'm getting the force of the aluminum as 156.9 kips. We did great. We now know that the aluminum is supporting most of the load. The steel is supporting some too. But we have to find the stresses. If you read the problem, they want to know the stresses. Okay, well, we can do that. I just need some room. I'll make some room over here. There's all kinds of room over here. if you just tuned in, we're doing problem 4103. We're finding statically indeterminate stresses by using compatibility equations. But right now we're going to get the stress in the aluminum. Stress in the aluminum, well, you just take the force, the 156.9 kip, and you divide by, I think it's 3 pi. Didn't we decide it was 3 pi for the aluminum? Okay, do that. Let's see what you get. I'm getting 16.65 KSI. Okay. Did it go, did it yield? Well, I don't think so. Aluminum doesn't yield till you get to 60 KSI. We're only 16.65 KSI. So the aluminum doesn't yield. Now let's do the steel. Need a little room in here to do the steel. We're doing the stress in the steel. Well, it's 143.1. I think the steel just has pi square inches. Remember when we did the area of the steel, it was just pi square inches. Do that. Let's see what we get. I'm getting 45.55 KSI. I need an on that. I need an on that.
That's what I got.
That's what I got.
Now here's a problem, guys. Steel yields when you get to 36 KSI. You will never get a 45.55 KSI stress in steel because it yields at 36. Do you understand? You can't get to 45. So I've just figured out what happened. The steel yields, but the aluminum doesn't. That doesn't mean the whole thing collapses. The steel is still supporting. That's the beauty of steel. Even when it yields, it's still providing support. That's why it's so wonderful. The aluminum has not yielded at all. It's got 16 KSI, and aluminum doesn't yield till you get to 36 KSI. So let's put the final answers up here. Those answers that we got are no good. We can just cross them out. Everything we just did is no good. I can tell you what the stress is in the steel. It's equal to the yield stress of steel. It's equal to 36 KSI. Now we're going to get the actual force that the steel supports. Well, the way to do that is you take the stress of the steel times the area of the steel. What is the area of the steel? Well, isn't that the pi square inches? Take 36 KSI and multiply it by pi, and here's what you'll get. You will get 113 kip. 113,000 pounds. Now this statics equation is still good. The force of the steel and the force of the aluminum have to add up to 300. So I can get the force of the aluminum. I can almost do that in my head. I think it's 87 kips. Does the 87 and 113 add up to, no, it's 187, isn't it? Do those two add up to 300?
Yeah.
Yeah, that's it. Okay, now let's get the stress in the aluminum. Now the stress in the aluminum will be 187 kips divided by 3 pi. Okay, do that with me. Now those are square inches. And we'll get the stress in the aluminum. I'm getting 19.84 KSI in the aluminum. Remember the answers that we got before? We got 16 and 45. Well, those are wrong. The correct answers are 36 and 19. Now look in the back of your book. This is 4103, and let's see what they said. 4103. They said 36 and 19.8. Hey, we got what they got. How about that? They, in the back of the book, they said that the stress in the steel is 36 KSI. If you don't believe me, look in your answer book for 4103. They said the stress of the aluminum is 19.8. Well, they rounded off. We're happy. We just did a statically indeterminate problem. This one here was different. We found out that the steel yielded. Do you have any questions on that? Well, okay. Now, according to the schedule, we're supposed to start on chapter 5 next time. I don't want to get behind. There was something I wanted to do in this chapter 4 that we haven't done. Maybe I can sneak that in next week, but you've got some homework to do. One of them is with the thermal stress that we talked about at the beginning of our class. But we only have about 4 minutes left, and so what I'm going to do is that's not enough time for me to really do much. I'm going to sign off till next time, unless you have a question or comment. I'm going to say goodbye for now until next Tuesday at 9:30.
Professor, real quick, I have a question.
Sure.
For the force of aluminum being 187 kip, where'd you get that number?
Oh, thank you so much for asking. What I did was I subtracted 113. See, if the steel is 113 and you subtract, you get 187. Does that make sense?
Yeah, that makes sense. Thank you.
They have to add up to the 300. Anybody else? So glad you asked. Well, I'm going to click this little button and say goodbye for now, everyone. Bye-bye.
Bye. Thank you very much.
Bye-bye. Thank you very much.